Hello, I'm Gabe, and today I'm going to be talking about magnetoreception, that is, the ability of living organisms to detect magnetic fields. We often speak of having a sense of direction, but it never really made it into the list of the 5 senses that we learned about in school. In the last few years, and especially in the last year, this has been a hot topic, and we're getting closer and closer to understanding how this 6th sense works. One recent study from Japan, linked to in the description, produced this video, which shows a magnetic field having a chemical and quantum mechanical effect on cells. But how did scientists end up going down this path in the first place? For more than 100 years, we've known that migratory birds are able to find their way to the same places year after year, even when blown far off course to places they've never been before. Carrier pigeons are also famous for being able to find their way home from any location on the planet. So, scientists strongly suspected that they had some way of sensing the magnetic field of Earth and using it to navigate, and studies have borne this out. We have good reason to believe that sharks and whales also have such senses. More recently, we've also discovered that dogs seem to be able to sense magnetic fields, to the point that they prefer to both sleep and poop facing a particular direction. And one recent experiment seems to indicate that some, perhaps the majority of humans, also have such a sense, and though not consciously aware of it, are able to use magnetic fields to navigate. A recent study showed that some percentage of humans were able to navigate to a food source when hungry, given only a magnetic field to guide them. It's not surprising that living organisms would benefit from being able to detect magnetic fields. Earth's magnetic field has remained relatively constant for millennia, making it an excellent aid to navigation. So, evolutionarily, it makes sense that organisms that can sense magnetic fields would be better able to compete. But how could this work? Unfortunately, we still mostly don't know. It's been called the biggest mystery in sensory biology of this century. But there are 3 leading theories. One theory relies on a protein called cryptochrome. Precisely how this protein allows organisms to sense magnetic fields is not known. We just know that it is sensitive to magnetic fields and also light, and it shows up in many organisms that seem to be able to sense magnetic fields in areas where we suspect their magnetic sensors are located. For instance, humans have this protein in our eyes. Another theory involves the mineral magnetite, a natural occurring mineral that happens to be magnetic. We know that many organisms carry magnetite crystals within them, and we don't really know what other function these could serve. Humans also have magnetite crystals within our cells. The third theory emerged only in the last few years. It involves symbiosis. Some bacteria have structures which we know to be able to sense magnetic fields. They use long chains of magnetic structures, which we call magnetosomes, and we refer to them as magnetotactic bacteria. A recent study linked to in the description shows how some protists have been observed to have a symbiotic relationship with some of these bacteria, which helps them navigate. It's possible that some larger organisms may do the same. Humans, for example, have some of these bacteria in our gut. If true, it would give a whole new meaning to the phrase following your gut. Regardless, which of these 3 is the real explanation, if indeed only one of them is not really well understood. But this animation and the related paper certainly have improved our understanding somewhat. So, what is it that we are seeing here? What is going on? It relates to the first theory I mentioned, the cryptochromes, which humans have in our eyes. To be precise, cryptochromes are a class of flavoproteins that exist within a larger protein called a cytochrome. One particular cryptochrome is known to fluoresce when exposed to a certain wavelength of blue light. That is, it produces light, in this case green light, when blue light is shown on it. And that is the glow you see in the video. What scientists tried was altering the magnetic field the cryptochromes were exposed to, and they found it changed how quickly they fluoresced. When they turned the magnetic field up, the fluorescent reaction happened measurably slower than when they turned it down. At first, they weren't sure how this could be happening, but they have since come up with a theory. When the blue light hits particular atoms in the cryptochrome, it collides with some of the electrons, boosting them into a higher energy state. Normally, they would quickly return to a lower energy state and release another photon, in this case a green one. However, while in their boosted state, the cryptochrome molecules form what are known as radical pairs, aligning with one another so as to share their excited electrons. This is where quantum mechanics comes in, as electrons also have a quantum property called spin. And cryptochromes can only form radical pairs if the 2 electrons in question have opposite spins. And they can only separate again, and the electrons return to the low energy state, if the electrons continue to have opposite spins. But magnetic fields have been observed to change the spin of electrons. So if the electrons in the cryptochrome are being excited by blue light, and then before they can return to a low energy state, one electron's spin is changed by a magnetic field, they can't so quickly return to that low energy state, slowing the fluorescent reaction. Many papers have come out in the last year talking about how this could work, but this is the first study to actually show it happening in real time. And it didn't take a very strong magnetic field to create this effect. The magnets used in this study to alter the magnetic field were no stronger than your average refrigerator magnet. The unit we use to measure magnetic field strength is a Tesla, and these magnets measure about 25 millitesla, or thousandths of a Tesla. The magnetic field of the Earth is many thousands of times weaker, but it can still affect the speed of these reactions. Even so, this only tells us that the speed of certain chemical reactions may have a role to play in how organisms detect magnetic fields. We have yet to understand precisely how this translates to a magnetic sense of direction, but the number of studies that have come out in recent years seems to indicate that we're getting very close indeed to such an understanding. For now, that's all we really know. It would be quite something if we could not only figure out how mammals and some humans can sense magnetic fields, but perhaps how to train ourselves to sense them consciously, and not just when we're hungry and happen to know there's a sandwich nearby that happens to be surrounded by a magnetic field. This video is a rewrite of a video by Anton Petrov of What to Math, an amateur science communicator of Russian extraction born in French-speaking Canada who currently resides in South Korea. He also has a video about the magnetic field sandwich experiment. The link is in the description. His ability to read a scientific paper nearly every day and translate it for the masses using copyright-free images and videos is prodigious, but sometimes he's a little hard for native English speakers to understand. I'm Gabe Heller, the son of an English professor with a great interest in space and sciences. If you have similar interests and enjoyed this video, let me know and I'll make more. But even if I don't, I'm sure Anton will, so please also check out his channel, What Da Math. Subscribe if you haven't, let other folks know about it who share your interests, and support him on Patreon or by purchasing one of his wonderful person t-shirts featuring a great image of light curving as it passes near a black hole. Bye for now.
Just to let you know, this video is over soon. So rub your eyes and scratch your thighs and sing in tune. It's time to find another kind of video, for this one is nearly done, you know.